again, and I'm not so tired, so I'm going to try this again. This stream is going to be all about the Ackermann function, specifically an implementation in C++. I'm going to go back into the virtual machine I was using yesterday, which is right there at the moment. This is a VMware player, and it's running Ubuntu 64-bit, and I'm running the i3 window manager because I prefer it. If you're wondering why the host machine isn't actually Linux, this is actually my gaming machine, so I have to have Windows on it for gaming. But there is a slight problem. That looks rather small, and I can't remember which resolution I used last night. It may well have been that one, 1920 by 1440, so we'll just change it. 1920 by 1440. There we go. That it doesn't fit my screen. My screen is 2560 by 1440, but this virtual machine simply won't go to that. What else do I need? I need an editor. And last night I was using gedit. But I don't like gedit that much. But I will just go back to it, and I will perhaps resize this. Oh, I'm not going to be able to. There we go. So we'll just clear that, and we'll just open what we were doing last night. So C++, and yeah, what I was trying to do was let you look up an Ackermann result. So we had an ACK result, the M and N and the result, and if we went in and M was 0, we could instantly calculate it and push that result back to the vector for storage. And then if we were going to have to look it up in either of these where M is not 0, we could try and look it up rather than calculate it. This was to speed things up, to put it bluntly. And it wasn't the best thing I'd done. It wasn't the best thing ever. It looks quite awkward to read on the screen, but I'm trying to wrap the text so you guys can read it as I'm working on it. I hate it looking like this. I'll be honest. I wish that I used a better editor, but for now we'll stick with that. So this is the result. We're looking up that. If we haven't looked it up, we do need to calculate it. Okay, but hopefully eventually we'll get back to a result that we can store. I may change this in a moment, but what we'll do is we'll apply the lookup here as well, where we've got an Ackermann within an Ackermann, and we will go if lookup mn minus 1 l result. Okay, then we know we've got the inner result. Actually, I'll actually call it that. Inner result, and we'll initialize it at 0. Inner result. And what we'll say is, if we couldn't look it up, we'll go inner result equals ACK mn minus 1. So that's trying to save us some time to calculate just this piece here, just the inner result. And if we can cut that out, then just there we know that the answer is now inner result. We're still recursive, but not within a function within a function. We're not passing a function's result as the parameter directly. We are placing that function's result into a variable and then carrying on. And that's an important step. It means that we can defer processing this one until the first one is complete. And well, that's important for me to do. Let me just move something over here, actually. We have a viewer. Hello, viewer. So yeah, that's the inner result. And that's how we'll be using it. So that's that piece. That's the second piece. Now the second piece then, again, we can look it up. We go if not lookup m minus 1 inner result, then we've got to calculate the inner result. at the outer result. So that's result equals acc m minus 1 inner result. Da, 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 da. Yep. So that means we couldn't look it up. Okay. So we can get rid of all them. And this outputting is a little bit random now. So what I'm going to do is just have the already calculated stuff somewhere else. I'm going to go if not look up there. See, I was tired. That is why you don't program when you're tired. So we look it up, otherwise we calculate it. It's as simple as that. Look it up or calculate it. Look it up or calculate it. Look it up or calculate it. Just to speed things up. And we've removed all the output from the middle of the ACK function. So that's it now. That's the ACK function we're going to go with at the moment. So we are putting in one, putting in the other, having no result. If it's 0, we immediately give us the result and push that result back to the vector. Otherwise, if it's any 0, we calculate the single child or look it up. Otherwise, we got 2. So we do the inner one followed by the main Ackermann. Okay? And the problem, of course, is that we're still within. We are not queuing these up in some way to be processed later. This Ackermann here cannot complete until that Ackermann has completed. But we are at least not going down 2 levels on the stack. We aren't pushing a return point for the inner and then a return point for the outer values. There aren't, nesting too many. We'll be nesting 1 less each time. So previously, when we increased the number passing through this loop, we got a stack overflow exception where we'd gone into so many copies of so many copies of so many copies of Ackermann, we actually couldn't do it in the language. The language actually failed on us. The language and the compiler was unable to handle letting us have so many nested entry points. So that's good. So that's all that. We'll look it up. Blah, blah, blah. Found is true. So just here we'll go cout found m n equals, and what did I call the resources? Pointer r. Right, so that's a found one. We found it. Found it. And then this one is where we need to just ignore it. So this is going to output Ackermann's it's going to return. Yeah, so we'll go to here and we'll say int the result. We'll say the result is an Ackermann. Cout ack over m n equals l the result. And that's just going to output anything we actually get a result for. So let's clear this again. C++, std equals C++14. Oh, we're in the wrong folder. CD C++, ls. There it is. RM Ackermann, just to make sure it's gone. Yeah. C++, std C++14, main.cpp, out Ackermann. And what do we got? Oh yeah. And this is result. So yeah, just on that second one, the outer result we needed to put, that's lookup needs to put its result somewhere, otherwise it doesn't know where to put it. and the other one we're looking up the pointer or the memory point of that. There we go, it's clear now. Clear, just rebuild, Ackermann. So these are all lookups though. These are all found lookups. We're not recalculating them. We've calculated them once. There's an awful lot going on that was given away the first time. So these are all values of Ackermann that we've calculated. And it's quite impressive that it's doing this amount of processing. Obviously, if we weren't outputting to the console, it would calculate a hell of a lot quicker. And something that we could do to speed up this whole process is, well, perhaps loop through all the rank with M0 values and pre-calculate them. That would be a good step. Once you've pre-calculated those, you could pre-calculate all the ones with N-1. But pre-calculating and storing the values is something we'd have to do over time. We'd have to store these results somewhere, probably a database or some structure. We'd have to put them somewhere. It's the dogs. Hello boys, come here. It's the dogs. We've got 5 dogs here at the moment. I've got a message. Oh. It's a machine from work texting me to tell me it's all right. So there you go. We saw that go up to 2,000 to drop down again. We're seeing higher and lower numbers appearing as this is doing its thing. Excuse me. I will just kill that off right there, and to speed things up I will put that out to dry. So that is just removing that lookup found. We've seen it running, so look, that's how quick that now went without having to output all that stuff. That's how quick we've got to Ackermann 4.0. We were still in the 0.0 ranges when we were just looking at before. Hang on a second. Monty! Bunny! Come here! Ibati T. Loa. Hello, Ryalayo. I've no idea what Ibati T. Loa means. You tell me what that means. But yeah, so we're still calculating this next Ackermann. This is Ackermann 4.1. And as you can see, Ackermann 4.1 is taking an awful long time. Even using the lookups, it's taking an awful long time because we're constantly having to cycle back through everything we're looking at before. Now, if you were calculating this each time, you're throwing away all these results. You're not actually storing them. So it's pretty bad. If we were in Windows, we'd be able to show you a process status, but I don't want to open ptop right now, so we'll leave it there. But yeah, Ackermann 4.1. So the question that goes around the internet a lot is, has anyone ever calculated Ackermann 4.2? Well, Ackermann 4.2 is something that we're aiming to calculate here, well, not today maybe, but in this sort of bit of research that we're doing. And I believe I'm going to have to improve this lookup. Because this lookup, if we look at it, it's a loop. It's just a for loop. We're just going through every result. And what we could perhaps do is categorize the results. We could say that put all the ones with M0 in one table and put all the results with M1 in another table, so on and so forth. So we build up a structure to how they are. And then we could subdivide the M's and the N's to look them up better. And this is pretty much how when I first learned about computing, we learned about, I think it was the British Telephone Directory, actually having to massively parallel out their search algorithms. And obviously nowadays we could probably search from the beginning to the end of the entire telephone directory with one for loop and not have to worry about the processing time. But here, look, this is something where we would have to process it out. We would have to work out a way of breaking things down and structuring the data. And they're the two parts of it. There's a structure to the data that you're collating and a structure to how you look at that data. And I think when I learned about it, they only talked about a structure to how you look at it, because everything almost exclusively everything was still stored in a linear fashion. Big spools of tape were still the big mass storage devices of the time. I'm just looking around for anything on my piles of junk, but the floppy disk, it wasn't sequential access, but lots of the programming that I personally was taught on it was. We were taught the Pascal programming language, where you'd have a record and you would write each record in turn, and of course a record would very much echo an old punch card, and of course an old punch card was synonymous with mass tape storage. But anyway, I'm hoping this gets to Ackermann 4.2 before I'm old and grey. It should come up very soon. I haven't timed it recently, not with this lookup in it, but the lookup is a bit quicker than calculating it out. So it should still be running. So what I may do next is we're going to change this lookup stuff. Okay, we're not going to change it until this has got a result, but we're going to change this to store anything with rank M0 in one place, rank 1 in another, rank 2 in another. We're going to invent something to help us structure these a bit better. We're still going to do a linear search. I'm not sure what would be quickest. It might be quicker to have M as the key and then a tuple of N and R, so we can instantly jump to that value. But I'm not going to worry about that now. I'm going to do some very simple stuff for you guys. We will talk about tuples and hash tables later. For right now, it's just a vector, and I'm just storing the numbers and then looking them back up. But of course, the wasteful thing here is that if M and N are not in the results, we have to go through all of the results to find them. So that's taking more and more and more and more and more time. As that list of numbers results gets longer, we're having to parse through every one of them to confirm there's nothing there, which is where a hash table comes in. A hash table will let you jump to a result before you need to do all of this. Right, I'm bored of that. So, that's the appalling properties of Ackermann, pretty well pointed out. As I say, Computerphile with Professor Brailsford do a much better job of this than I do. But I'm just interested in improving this speed now. So Ackermann 4.1 is the best I've got to with all this. My mouse is playing up. I've still got this horrible mouse because this one died. I'm waiting for replacement parts for this one because I love that one. So I need, what do I need? I can't remember now. I need a C++ thingamabob, what's I call it? Let me check my notes. I need a std tuple. Where's my tuple? There it is. I can't remember what I'm doing with this. Yeah, that's my tuple. Right, so include tuple and the structure. Sorry, the tuple is whatever it is. So using what should we call it? The nr equals std tuple int. So the int is really the n and the result of the actual value. that we're calculating. But this isn't good enough because you know, we just don't know what's in that. So structure, oh sorry, class result list, or it's actually going to be a result vector, but you know what I mean. And it's going to be public, and we're going to inside it, well, wherever, std vector nr. We've got lots of nr's in it. In fact, we don't need an nr, it's a hash table, sorry. Sorry, my notes are all over the place. Unordered map, it is an ordered map. I prefer to have an ordered map. So it's a map. No. Let's just search for std hash, and I don't want to search for std hash. I want to search for map. There we go. If you're wondering what I'm looking up std reference, which is, can you see that? It's just minimize everything on my other screen. Can you see that? Yeah. So I'm looking up these pieces. So I'm looking at the map. There's a pair of things, and the pair will be something different. Try in place. Okay. Try in place insert secure if it doesn't exist. Okay, fine. Basically, we then want a set of pairs using result pair, std pair, and that's the int to an nr. So the nr then links to the pair, and this is the key then for our table. So std map result pair. I think that's how I declare it. I just need to check. It's the key to the T. So no, it's not that. It's actually int nr. So this is the results, and we can go constable get result, and we can pass it const int m, const int n, const int, no, it's not const int, it's the int address result. And what else does this need? We need to know const int m result list const int m so this just sets up the result list, how we think they should be. We're going to have the result pair linked to an M pair, and this is going to do a get result. This is replacing, hello whoever's just joined this screen, this is replacing this lookup through the loop. So we're not going to look through the loop anymore, we're going to use the map and jump straight down to whatever we want to jump to. And so let me go back to my reference. So here we are. Excuse me. I want to just check for empty as well. Is there an empty? Yes, there's an empty. So I want to know if it's empty. We know we're not doing anything. That's the first thing. So bool L result is false. Return result. So we always return something from this function. And we go if m equals 0 and m equals, this is confusing, this m, so that's this one here. So I'll actually make them parameter, name them parameters just to help you. equals parameter m. So, you know, you can't get a result from this if the m is not correct. That's the idea. There are two keys we're effectively looking at. We're going to separate these later, but effectively we'll just run through as we do the lookup for the m's at the moment for whatever we're doing. Then we use the actual map. So we need that, and we need to know that results empty is false. So we could go equals equals false, but I'll just go if not empty. Simple as that right now. And let's pop back to the map. We want to just see, we don't care about inserting, we want to find an element with that specific key. So we don't want to change the key comp, we don't want to change the value comp. They are integers, they're going to be fairly fine. These searches will be fine for those. But we do want to find the tuple. So this will find us an iterator. Okay, so we find whatever, we're going to use an auto. If it's not the end, then we found the second piece that we actually want. So auto find result equals results.find parameter n. So remember, the first part of the map is m. In fact, these are wrong, aren't I? I'm doing this backwards. I am doing this backwards. These are two integers. That is n, and that is result. So this pair isn't really needed, nor really is that tuple. We're not going to touch them at the moment. We don't need to worry about that. I got ahead of myself. Still don't know what that says. Rilo ho. It's a message from earlier, I think. Ibati ti loho. He said it again. I don't know what that means. Sorry. So auto find result, and we want to go if find result not equal to results dot end. So if it's not, you know, beyond the end of the structure, then n was found within this thing, and we then know that the value for p result will be the second part of this. So we can go, in fact, folks, that needs to be a pointer, int pointer. So we can go the dereference of the result item equals find result second. Okay, so that's taking this piece here, equipped. Oh, it's not actually a bracket, but it's a property. So if we're not at the end, we're returning the second piece. Simple pimple. And we're done. There is no loop there. There is no cyclic item. There's nothing re-entrant. We're just going to get that result. But we do need to also store a result. So void store const int n const int result. So we're going to just pass in a result, and again we will just if so if not results dot empty. In fact, I don't need to worry, do I? I can just use this try in place, which is new. Or can I yet? Let me go back. Try and play C++ 17. That's a shame. I'd have liked that. Insert or assign is fine. Insert in place. I'll have to find it first and then insert it. Construct the element in place. Make pair, yeah. In place, make pair. I want to know it doesn't exist first. So we want to insert unique, basically. So we'll go if, and what do we care about? We only care about results not being empty. First off, again, wish I was using a better editor. So if it is empty, of course, we know this is the first thing we're adding. Results.insert std make pair int pn p result. I think that's correct. No need for the int there. It's just a pair. So we're inserting that result. So the next piece, auto find result equals results.find pn, and only if find result equals result.end do we then do this exact same line. And that's just to save us some time, just to effectively store it uniquely, insert it into this map uniquely. Before I go any further, let's build that, make sure we've got no bugs, and we've got plenty. P result not declared in this scope. Let's have a look. That is stuff at the top. Map in a map. Haven't included it. Hash include map. Go again. Const bool get result expected bracket. What's wrong with that? Expected open brace before. Is that? Yeah, I'd forgot to initialize that. Store P result not declared in this scope. That's because it's not a capital R. It's a lowercase r. It's that. And the final one is the same thing because I pasted the line. There we go. Hello, new viewer, whoever you are. You can speak to me and I will talk to you. Hello. Yeah, so there we go. This is not doing anything yet. We've just got a result list. So what I want to do is have a vector of result lists, I think. Yeah, a vector of result lists. So we technically don't need that anymore. So I will just take them out. And this is not a vector of those. Static vector result lists. And I will take that out of there. There they are. I hate this mouse. So get result is fine. Store is fine. So this doesn't need to do this anymore. We know we've calculated here. We know we've calculated something. We can literally go into the list of results and store it, and we go for auto lists equals result lists dot begin lists not equal to result lists dot end. I've already spotted that I've put result lists, so we move to the next list each time, and this is where I'm going to improve it later. This still needs a loop through, but we're actually going to use another map of these lists later to jump straight to the M list. We're not actually going to spin through and look for each one. What would I call it? Let's have a look. I called it result list, definitely. So it's not results there, it's result lists. Bye bye viewer, you've gone. Oh well, I must be dead boring, but I'm interested in what I'm doing, so this is why it's being broadcast. Just so you can see my lovely face as I figure this shit out. I'm going to come back and do all the CPU stuff later, which I've already been through, so that'll be a lot better than this. But this is all just a test to see what works best. I need to work out why this side of the screens still have got black borders. It's because of this resolution problem, so it's no big deal. And if the list m equals m, so if that is this list, then we can go what can we do? We can go pointer list store store n result. Okay, so because we need to know the result, there we go. Because we know that is that, we do all that, and if we didn't find it, sorry about that, folks. There's only one of you left now. Sorry, I obviously got really boring answering the phone, but that was important. So yeah, we're looking up this value, and if we don't find it, it's going to insert it into that location. If we didn't find an M though, we do need to say create one, don't we? This mouse is annoying me. We need to perform this and insert it. And what we'll do for that at the moment is just here. We'll go bool L result list found false, and this is result list found true. If not, result list found, then result list, new list, m, new list dot store, and result list dot push back new list. So we always store in the current list, or we create a new list. Simple as that. That's now made that a lot longer than just the 3 lines before. This though should get smaller because we can just look it up the same way, and we do that with get result. I'd like to perhaps look up a bit better than that. So look up this. So look up for auto list equals result list dot begin lists not equal to result list end list, and then if list m equals m that we've passed in, then L found equals true. Well, no, it doesn't equal true. It means we found the right M. What do we do then? If we found the right M, we look it up in the actual list with get result in the list, and we do if list get result. Yeah, I think that needs to be a dot there actually. That needs to be a dot there. This needs to return, well, M is, it's not actually a bracket, is it? Duh. It's just the value M within it. So if get result, and we pass it all 3 parameters again. M, N, R, found equals true, and break out of that loop. Otherwise we didn't find it in the lookup, we don't care, we've got nothing to do. This stops us looping. We're still looping through all the lists, but we're only looping from all the 1s to all the 2s to all the 3s to all the 4s to all the 5s. We're not looping through every single 0 to get to every single 1, to get to every single 2, to get every single 3. We're chunking it up. This will be another table lookup eventually, another map lookup. Hash table lookup rather. So this stays unchanged, I believe. Yeah. If we don't look that up, calculate it, blah 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 blah. Let's give that a try. And page number 25 results there. I got that wrong, haven't I? So 25. There's no go to 25 on this. That's really annoying. I've picked the real wrong editor, haven't I? I need to go in a moment anyway, so for now that's probably going to be all I'm going to get to. pointer list, list was not declared. Where's that? If scope 76 in lookup. Lookup lists, do that, and then that's in Ackermann lists plus lists. Get rid of them. And then in Ackermann result lists was not declared. There we go. So it jumped down to 4.0 fairly quickly there. In the background now it's running. Right, I'm going to actually leave that running. That is oh. So I'll leave that running and I will go sort the Wi-Fi out. I will Well, I had expected in the time I was gone that to have got Ackermann 4.2, but it hasn't, has it? It hasn't made a significant difference. Let's just do a new. Get my notes back up. Let's just do a standard. What do I need? Include iostream in main. Don't care about anything else. Int ack const int m const int n if m equals 0. We're just going to calculate, aren't we? So it return, is it n minus 1 or is it n plus 1? Else if n equals 0, return ack, is it n minus 1 1? Else return ack m n minus 1. And we're going to go for int a equals 0, a equals 6 plus a, for b equals 0, b smaller than 6 plus b. That's not a for, it's an int. SCD, cout, ack a, b equals, and then we call ack a, b, so that is the standard version. Save as standard, and I want to leave that running, so let's have another one. This isn't responding correctly to doing a new vertical. Hang on. I love it when people that aren't here start giving you tasks to do. It's like really annoying. Why isn't this doing verticals, everybody? I go to that one. I think it's not doing verticals either. Whatever. So we have the standard U plus STD equals C plus 14. Standard CPP output standard STD end line. Go. Standard. So there's Ackermann. That's not right. That's not right. They don't just equal 2. I've done something wrong there. Where's my result thing? Oh yeah, of course I have. That's not n minus 1. it's the Ackermann m minus 1 of the Ackermann mn minus 1. That was a bit easy to compute for a second there, wasn't it, folks? There you go. So it's sat at 4, 3 as well. So there, the numbers are the same. I'm just looking. They're the same. You could almost convince yourself there's a pattern with these, isn't there? You could almost convince yourself that you can see that any rank. Well, there you go. So the standard Ackermann has got 4-1, quicker than mine, a lot quicker than mine. So my lookup stuff is crap, a lot quicker than mine. That's bad because mine was meant to make things quicker, but it doesn't. It clearly doesn't. Okay, right, that's an hour of this nonsense. I'm done for now. I apologise for that break in the middle there, folks. I will now have to go and do something because she who must be obeyed has phoned. And I will come back to this in a little while. Bye-bye.